I want to give you just a real brief, basic explanation of Ohm's law, which is kind of the foundation of direct current circuits, also known as DC circuits. And so here's kind of how it works. Here I have a little light bulb. Here I have what's called an electric cell. And I'm going to connect one end to the other. So you put this right here, and you can see that the light bulb glows a little bit. Not very much, because this is only 1.5 volts here. I'm going to explain what voltage is here in a little bit. But our robot runs on a 12-volt battery, and it's a lot bigger than this, a lot heavier. But size does not indicate voltage, right? Have you ever seen a little 9-volt battery? It's way smaller than this, and yet it's 9 volts. So we're going to talk about what voltage means and current, and then we'll get also to resistance. What does resistance mean? And then we'll define Ohm's law, and then we'll work some problems. But here's basically what you got. You got a battery. Let's just draw a battery like this. Kind of make it look like the battery on the robot. And it's got a little terminal here and a little terminal here. And we say, oh, we'll call this the plus terminal and this the minus terminal. Okay, and then what do? Well, we hook it up to this thing called the power distribution board. Did I say that right? Okay. All it is something that lets you hook up more than one thing to the same battery. But let's just, we're going to take this wire and this wire, and we're just going to hook it up to, how about this light bulb? So here's my little light bulb. It's got a little thing like this, and yeah, looks like that. And inside, there's a little filament, and energy is transported from the battery through the wire into the light bulb. That energy is dispersed into the world, and then it comes back to the battery to pick up more energy. Okay, so here's what you need to understand. A battery stores energy. We've talked about energy before. Energy is the capacity to make change to the environment. If your battery is depleted, if there's no more energy stored in your battery, your robot can no longer make any changes. Or at least maybe there's a little bit of energy left, but it's not performing very well. So, but if it's fully charged, it contains energy. Now, before we get to our definition of voltage, which voltage is a measure of how much energy there is that comes out of the battery per unit of charge that's pushed through the wires. Let's define what charge is. Let's take a little microscopic hunk of this wire and look at what's going on inside the wire. So here's my wire, and not drawn to scale. Okay, the wire just goes like this and like this. There are atoms, copper atoms. So I'm just going to draw a few representative copper atoms. These are the nuclei of the copper atoms. Now, surrounding the nuclei of the atoms, you have electrons, right? You learned about that in chemistry. Electron clouds, energy levels, and stuff like that. But in all metals, and most of the periodic table is metals. In all metals, the outside electrons are held very loosely by the atoms. So let's say in copper, let's say for every atom, there is an electron that is free to move. Now, when there's no current flowing, remember, and by the way, for every valence electron in the wire, there's a proton in the nucleus to match it. So wires are electrically neutral. They have just as many protons in the nucleus as there are electrons in the electron clouds. Okay, they do not have a net charge to them. Charge is what electrons carry and protons carry. And you probably learned this in chemistry, that protons repel other protons. Have you learned that before? Protons repel and electrons repel electrons. But what's true about protons and electrons? Okay, they attract each other. There's a force that brings them together, which is called Coulomb's law, but we're not gonna study that. We'll study that in physics. But what happens when there is current flowing through the wire is that there is what's called an electric field that is pushing the electrons through the wire. So now someone closed the switch. Now before you close the switch, let's put a switch in here. So this is the switch that's on the robot. And here's the symbol for a switch. It's just a break in the wire, right? This is called an open circuit. That is, the path that the electrons flow through is open. Oh, if there's an opening in your circuit, they can't flow. They can't move. They get stuck. But when you close that switch, when you close the switch, and you know what that little switch on the robot, when we turn the robot on, we're closing the switch, and now all of a sudden these electrons, if there is something going, it can flow, and little lights can blink, and motors can turn, and all kinds of good stuff can happen. Well, when that happens, when you close the switch, the battery supplies a force that pushes these electrons through the wire. Okay? And so they start flowing. Now, how fast do you think electrons flow through a wire? A lot of people think, the electrons flow at the speed of light. That would be wrong. The electrons do not flow at the speed of light. In fact, they flow very, very slowly. A snail moving across the sidewalk, a wet sidewalk, hopefully, is faster than the electrons flowing through this wire. What does move at the speed of light is the push on the electrons from the battery that travels close to the speed of light. It establishes what's called an electric field that pushes all the electrons throughout the wire. So what happens is, it's kind of like water in a hose. If you've got a hose with water in it, and you turn the faucet on, the water in the hose moves fairly slowly, maybe a few inches per second through the hose, maybe a few feet per second even. But the push on the water is almost instantaneous, isn't it? I mean, if the hose is all the way full, you turn the faucet, almost instantaneously the water starts coming out the other end of the hose, right? Same thing is true with electrons in a wire. Since the wire is filled with electrons that are free to move, as soon as you close the switch, there is an electric field established that pushes the electrons through the wire. Okay? And the electrons carry energy. Now, if you have a big basket, imagine a huge basket full of electrons. This is now I'm not going to draw all of them. And because, hold on a second. And I want to reciprocate that. In fact, if I would have to draw, well, you know chemistry, right? Atoms are really tiny things. If I drew, I would have to have 6.25 times 10 to the 18 electrons. If I had this many electrons in a big basket of electrons, I would say that there is one coulomb of charge. Well, in fact, electrons are negatively charged, so we call it -1 coulombs. But the proton and the electron carry exactly the same amount of charge. So you can think of 6.25 times 10 to the 18 protons makes 1 coulomb of charge. Now, when they defined the coulomb, they didn't know that atoms were made out of protons, neutrons, and electrons. So the definition came from something else. But I'm not going to get into that. But just think of 1 coulomb of charge as being a huge batch of electrons that are flowing through a wire. Now, when you have a 12-volt battery, here's what we mean by voltage. What we mean by voltage of a battery is the energy delivered by the battery divided by the amount of charge that flows out of the battery. So energy delivered per unit charge. See, this battery is actually, it's this way, right? This is the negative side, so that the battery is pushing negative charge this way through the circuit. The energy delivered per unit charge. Well, what units do we use for energy? Energy is measured in? Not clamps. No, God, no. It's joules. Joules. Don't let James Prescott Joule down, okay? He worked very hard to get this unit named after him. Joules. And the units for charge, this big basket of charge that gets pushed through, is called a coulomb. Joules per coulomb. We have a name for a joule per coulomb. It's called a volt. A volt. Named after Alejandro Volta, who kind of discovered all kinds of great stuff about electricity. And so they named it after him. So, what does a 12-volt battery mean? Well, when this many, what is that? Roughly 6, a little over 6 billion trillion electrons are pushed out of this battery, they will carry 12 joules of energy with them, and they will deliver this energy to your light bulb, or to your motor, or to your speaker, or your computer, whatever is consuming the energy to do something. This is how much energy is delivered per unit charge, joules of energy per coulomb of charge that comes out of that battery. Okay? So now you kind of know what a battery does. Here's a battery. Look right there. Oh, I don't know if you can see it. Ooh. Oh, let me hit focus. Let's see. I want to hit focus. There we go. Oh, yeah. Glad I cleaned my fingernails. 1.5 volts. This thing delivers 1.5 joules of energy for every coulomb of charge. For every 6 billion trillion electrons comes out of it, it'll give you a joule of energy, which isn't very much energy, actually, right? But that's pretty good. Okay. Now, so you've got this energy coming out of the circuit, and it's being carried by these little electrons. They're like carrying little baskets of energy, and they come out here, and then they deliver their energy to the world. Poof. And then they come back and pick up some more. I am about to tell you something. It's makes me very sad to tell you this, because electricity is kind of confusing. When they defined what electric current was, and I'm about to define it, they didn't know that electrons were really going this way. What they thought was there was a surplus of electric fluid, thank you, Benjamin Franklin, He thought there was a surplus of electrical fluid that was actually going this way. And so what's happened is we have defined this thing called current. You have heard of current? Electric current. Yes. Well, now you're going to know you're going to learn what it is. Current. Current is equal to the amount of charge, actually I should say positive charge, that flows by per unit time. So if you're in this wire, let's take this cross-sectional area of this wire. Here's a cross-sectional area inside this wire, and you have a little measuring device, and you go, the electrons are flowing this way. Okay, electrons are flowing this way. Well, current is defined to be the amount of positive charge that is actually flowing the other way. In a wire, when electrons flow this way, we pretend in our imaginations that it's positive charge flowing the other way. Why? Why? I'll tell you why. Because Benjamin Franklin guessed wrong. What he thought was a surplus of electric fluid was actually a deficit of electrons. It's electrons that, in a wire anyway, carry the charge that moves in an electric circuit. But they had no way of knowing that. They didn't even know that matter was made out of atoms when they defined all this stuff. So we're stuck with this definition. It's too bad that he had a 50-50 shot and he blew it. He had one job and he blew it. If only he had named what turned out to be the electron and assigned that the positive charge, electricity would be a little bit easier to understand. Because by definition, it's the flow of positive charge per unit time. So if it's negative charge, it's actually flowing. We just reverse the direction. So anyway, let's do this. What do we measure charge with? Charge is coulombs. A big basket of charge. 6 trillion billion electrons is a coulomb of charge. How much of that goes by per unit time? Well, what do we use in science? What do we use for time? Seconds. All right. Now, so this is a coulomb per second. And we use a capital C to abbreviate coulombs. We use a capital S to abbreviate seconds. What is a coulomb per second called? You've heard of it because you probably already used the idea of what current is measured in. What is current measured in? What? No, not power. Amps. You've heard of amps? Amps. A coulomb per second is called an amp. Actually, technically, it's an ampere, but everybody shortens it to amp. And so we use the letter A to abbreviate an amp. Okay, here we go. Okay, so we got voltage measured in volts, and it's a joule per coulomb. We've got current that is now measured in amps. Okay, we're now ready to define our final quantity for the day, and that is resistance. So let's say I've got my battery right here. Let me redraw it. And I hook it up to something that's going to give off light, or it's going to be a motor, or it's going to take the energy out of the circuit. We have a symbol for that. I don't know what it is, so I'm just going to draw this little zigzaggy thing. What does the little zigzaggy thing represent? It represents something that's going to use the energy that's flowing through that circuit carried by the current, carried by the charge. Okay? And it can be a light bulb, it can be a motor, it can be a resistor, it can be just about anything that uses the energy in the current, in the electricity. Current is what we mean by when we use the word electricity. We're really talking about current, charge flowing in that wire, carrying energy with it. So anything that consumes the energy and disperses it out into the world somehow, we call a resistor. A resistor. Okay? It uses the energy carried by the current. And again, motors use the energy, right, to create mechanical motion, torque, movement. Resistive elements, well, I'll just call them resistors, defining resistors, but they give off heat. And by the way, sometimes when a motor isn't turning, what happens when a motor gets stalled, but it's connected to the circuit? What? You get magic smoke, because now the wires in that motor becomes like a resistor, and resistors give off the energy in the electricity off as heat. If the heat gets really hot, the insulation on the wires of the motor will literally burn. Burn, baby, burn, and give off smoke. And that's when you're destroying your motor. Yeah. So they can, hopefully that doesn't happen. They can be lights. Actually, motors, resistors, lights, they can be some kind of CPU or something like that. I'll just put computer. A radio, anything. Anything that uses energy and takes it out of the circuit. Now, ohms, for certain applications, it turns out that that if I want current to flow through this wire, I need to have a certain amount of voltage. If my voltage is 0, there's nothing pushing the current through the wire. So no current will flow and no energy will be exchanged or transferred. But if I put a little push on here, then some current will flow, and I will be able to put energy out into the world and do something interesting. But how much current do I get? How much voltage do I need to get current to flow through this resistor? Well, that is what we call resistance. Resistance. Resistance is, well, let me write it down here because just to make the notes look neat. Resistance the voltage needed to make 1 amp of current flow. I wrote it as a ratio. The voltage needed to get the current to flow. Now let's take a look at the units here. Voltage needed. What units are those? Volts. Make 1 amp of current flow. Well, that's current. That's 1 amp. That's amps. It's a ratio of volts per amp. Now we have a name for a volt per amp. A volt per amp, by definition, is called an ohm. Have you heard of ohms before? Right? Like how many ohms is that resistor? Well, what abbreviate? We use a V to represent a volt. We use an A to represent an amp. So what should we use to represent an ohm? Well, how about a capital O? Okay, that's great. So what if a resistor, we'll say, okay, this resistor requires 20 volts per amp or 20 ohms. You see a problem? Yes, there is a problem. An O looks like a 0. Well, we could say, okay, well, we'll just make all our zeros with a little slash through it, and then if it's like this, then it means ohm. No, we're not going to do that. No. So what we do is we say, well, I'd like to preserve the O to honor this George Ohm guy or something who discovered Ohm's law, and that's why we call it Ohm's law, because he discovered it. So we use a Greek letter O, also known as an omega, which is a horseshoe, basically. That's the symbol we use for ohms. It looks like a really awful, horrible cowboy hat. That's the symbol for an ohm. All right, now, one thing I've resisted, get it, using here are variables. So I'm going to create what's called a quantity chart, and then I'll give you an equation list with that quantity chart, and that will let you solve problems for a circuit. So stay awake and pay attention. Okay. All right. So we've got these quantities that we've talked about so far. Voltage, current, and resistance. Voltage, current, and resistance. So this is the name of the quantity. What variable do we use? In other words, what letter are we going to use to represent that quantity in a formula? Well, voltage starts with a V. So we'll use a volt, a V for volt. Capital V stands for volts when it's a variable. Current, we don't use the letter C. In fact, if you've never done this before, you'll never get, well, you got 1 in 26 chances. For some reason, I don't know why, and I've been teaching this for decades now, and I still don't know why, but we use capital I to represent the flow of charge in a wire, current. Capital I stands for current. Resistance, we use capital R. What's that? Maybe. I don't think so. I don't know. But I don't know. I don't. Look it up. I'll give you extra credit. Now, the variable, all right, so now we need units. What I'm going to do here is give you the unit, the abbreviation for the unit, and then how to think about that unit. So voltage is measured in a volt. It's abbreviated with V. And by the way, voltage is the only quantity I know of where the variable and the unit are the same letter. That's the way it worked out. But what is a volt? A volt is the way to think about a volt is a joule of energy per coulomb of charge. Current. We say that a current is an amp, and that's good enough for this class. An ampere, I don't know, an amp is good enough. We abbreviate with a capital A, and the way to think about that is a coulomb per second. How much charge goes by per second? Now, resistance is the hardest one to really grasp. It's an ohm, abbreviated with an omega. But the way I want you to think is, how many volts do I need to get 1 amp to flow through something? If something has very low resistance, that means I don't need a lot of volts to make an amp of current to flow through it. But if something has very, very high resistance, I need a whole lot of volts to make an amp of current flow through something. Okay? Now there's a couple other quantities here that I want to add that we've talked about. Here's the one. I want to talk about charge. Charge. We do have a letter for charge that we use that I didn't talk about before, but it's just a variable we use for charge. Now you would think you'd use the capital C for charge, but they don't. I don't know why we use this letter, but we do. Q. Sometimes lowercase, sometimes uppercase Q stands for charge. A big basket of electrons that we call a coulomb. And we do abbreviate that with a C. Now, a coulomb is a fundamental unit, but you can kind of think of it as being 6 billion trillion electrons. A little over 6, but just 6 billion trillion electrons, just a whole lot of them. More than you can count in your lifetime by, well, you need thousands of lifetimes. Let's see. Joule per coulomb, coulomb per second. I don't know. We could get a little bit crazy here and say seconds. We have time. Sure, why not? Time. We use the letter T for time. It's measured in seconds. It's a fundamental unit like that. Now, we do have some equations now that I want you to know and use to be able to solve problems. We have Ohm's law, which says that resistance is equal to the amount of voltage I need for a certain amount of current. And this right here, this equation, is Ohm's law. Let me show the man a little respect and capitalize his name. Ohm's law. Quite often, it's usually written like this. The voltage is equal to the current times the resistance. Voltage equals current times resistance. This is also Ohm's law. Either way, I mean, they say the same thing, right? It was kind of implied in the notes, but current is equal to charge over time. This is known as Kinney's law, right? Yes, because a man named Kinney, no, it's not Kinney's law. It's Kinney's over there. I was joking. All right. Mr. Kinney,
Can I say something?
Please. This is Mr. Kinney.
If you've got a hole in your schedule next year, or maybe your senior
E-Tech
year,
1,
most of you probably juniors here, aren't you going to be seniors? Why don't you consider taking E-Tech 1? If you're thinking, hey, I'm going to take a year off, a class off next
Go ahead and
semester,
take E-Tech.
consider taking
What?
E-Tech 1, project-based class. Wait a minute, this is engineering, isn't it? This isn't your
Yeah.
physics side. Never mind,
Thank you.
you guys have already got to
Yep.
but hey, you might
We-
consider taking E-Tech 1.
Take E-Tech 1, it's a lot of fun. I taught E-Tech 1, it's a lot of fun.
I have your tools. Oh, you
Yeah.
are. I'm just kidding. Yeah, I'm leaving now.
Okay, that was all recorded for posterity. All right. Now, but this is the one that you really want to use, and you're going to practice this. And oh my gosh, this is already 35 minutes long. That's more than enough. But you're going to be given some practice problems like this, where you'll be where you will use the given find and solve format to solve for either resistance, given voltage or current, solve for current, or solve for voltage. Yes, questions? I hate this class. That is all.